Okay, so let's continue. Let's build our square phantom. Maybe let's put a couple of more rectangles in, and maybe even this could be something. I think we could make something which is not really just multiples of 2 or something like this, so that it will a little bit go between pixels, so it's not perfectly aligned with pixels. That will help in avoiding inverse crimes. Let's put something like x is 1 over pi, and and second, maybe let's make something longer. And this would be in 2. And maybe let's even have here a little bit different attenuation. Let's see how this looks like. So now we have another one. And maybe let's have like one more and see. And how should we do this one? Let's see how this looks like. What do you think? Should we change it or add something more? Or
change orientation.
Yes, yes, good, much better. Let's do the third one horizontally.
So we're doing abstract thought.
Yes, yes. Maybe like this. Okay, let's try with this one.
That'll work.
Okay, cool. We can always change it later if we want. So that's our phantom, and then we should take a look at different data collections. So let's first just take a look at radon and iradon. Let's test various tomographic let's just put it like this. So then we need to use radon, or let's say, let's choose our projection directions, and maybe let's start with something like 0 to 179 with a step of 1 degree, so half a circle, and let's evaluate our phantom. So we need our phantom and then use radon.m to create a sinogram. So sinogram equals radon of our image and with these angles we chose. And then let's take a look how it looks like. Let's have a picture with 3 sub-pictures: the phantom, the sinogram, and the reconstruction. Because now in the testing, let's just use iRadon for the reconstruction, just to get an idea how it looks like. So in our first plot, let's just show the phantom. Actually, we can take it. Let's steal it from here. Okay, and this would be Tomo data test, for example. And let's do a second. And here let's show the sinogram. And these, I think, let's just comment and see what happens. Okay, so there is our phantom. Then there's the sinogram. Maybe, just maybe, it would look better to have the sinogram in its own picture, actually. So let's have here only the phantom and reconstruction in that picture. Well, reconstruction we don't have yet, but anyway. Sinogram in its own figure. Maybe we could here do it like here, size sinogram to the number of columns, and here the number of rows. Maybe we need to round. Okay, let's see how this looks like. Well, it's a bit clearer. So we have 180 angles, as we chose the number to be, 180 projection directions. There seem to be 49 X-rays in each projection. And that's the thing we discussed last time. MATLAB's Radon uses its own internal logic to decide how many rays it wants. In this case, it wants 49. It is possible, of course, to track down where this number comes from, but we will not do that. There we see our sinogram. Also, if we want, we can do this with a bit more accuracy. So now we have much more X-rays because our pixel image is bigger. So now we can see rather clearly the sinogram. We see there are 3 objects. Already from the sinogram we can see, in this case, pretty clearly that there are 3 objects, each drawing kind of a sinusoidal picture into the sinogram. So that's our data. But in our computational model, m equals AF, this will be a vector m where we just drop the columns in a long vertical vector. But this is maybe a good way to look at the sinogram anyway. Okay, the reconstruction is missing, so let's just use MATLAB's iRadon. iRadon is based on the so-called filtered back projection formula, which is the classical X-ray reconstruction method. We will not look so much into it in this course because we want to deal with the same matrix model covering many inverse problems. The filtered back projection is really built for the X-ray application in mind, and actually it even assumes that there is a lot of projection directions, so very small angular steps when collecting the data. So another reason of not focusing on filtered back projection is that we are interested in sparse data sets. And then filtered back projection is really not at its best.
Assume anything about the noise?
Not really. Filtered back projection, you can just start using it. How noise appears, of course, if data is more noisy, the reconstruction is more noisy, but then you can adjust the filter in the so-called, it's filtered back projection anyway. So in the filter, you can modify it so that it does not enhance high frequencies so much. So that's a way to reduce the noise. Yeah, and that process is really well understood by now, and I would even recommend the classical book by Frank Natterer, the grandmaster of filtered back projection. There, it's really all you need to know about it. And also his later book with Frank Wübeling as well. That's a great one as well. Okay, reconstruction. We apply iRadon to the sinogram and our angles. Now I must say I'm not completely sure if I remember the syntax correctly. So let's see here. Help iRadon. Okay, it seems to be okay. So also we want to so here we'll show the reconstruction. Okay, you see it's a very nice reconstruction. The values look okay, and although, well, we're not sure if this is on the same color map, but we have so many angles that filtered back projection is doing its job very nicely. We have lots of X-rays, lots of directions. Now, of course, if we, for example, if we take much bigger angular steps in our data, what happens is we have a more narrow sinogram, much less angles, and then the reconstruction suddenly is maybe not so good anymore. And now we have perfectly vertical rays and perfectly horizontal rays included in the data. We could do something like something like this. So no, it's still quite Let's go from pi. Pi is always good. So now we don't have such perfectly aligned. So you see there starts to be some problems. The values don't look so good anymore, and there are these kind of streak artifacts. And then also, if you go back to going with 1 degree steps, but we have limited angle case, then our reconstruction has trouble recovering all the parts of the unknown. And now we only have, in the sinogram, we have only part of the sinogram, not really spanning the full circle. And in practical situations, sometimes there are restrictions like these. And the tomographic problem takes many forms based on what kind of collections there are. So for example, we will study something like having maybe something like 20 angles only. So let's say something like 1 to 20, and then times something like 9 maybe, yeah, that sounds pretty good. Let's see what happens. So we have reconstructions like that. Filtered back projection is nice in the sense that you always get some kind of picture when you feed in data. Often you can really see the main features from it. So it's really it's for a good reason. It's the standard algorithm used in so many occasions. However, for sparse data cases, I think we can do better with the regularization methods we learn in the course. Yes?
I'm curious, if we were to take like a small sparse data, so
Mhm.
like small amount of angles,
Yes.
and take them from several points, like we had in the exercises or in the lecture notes earlier, that we had 3 close.
Sure. Okay.
Like this, and then
Mhm.
we attached 3 extra anomalies.
Yeah. So let's see if we, for example, if we have 1 to 10 and 30 to 40 and well, let's say 31, 61 to 70 and 91 to 100, something like this, for example. So our sinogram looks again rather cubistic, and as said, the filtered back projection will always return something, and often we can see some useful information out of it. So it will serve as our kind of baseline method to see if we can do better, and if we can see some different things compared to filtered back projection. But it's, as you see, it's nice and easy to play around with radon and iRadon. Just create some data, apply iRadon, and there is even the possibility to add some options here regarding the filter and some settings of the method. But now the idea would be to construct our measurement matrix. And we did have from a previous lecture, I think we had this radon matrix. So let's save this to our okay, so this should be let's say this is our first thing to do, compute some matrices for us to use, and let's save them into a subfolder data. So we are building matrices, and we want to choose the size of the unknown. So let's go first with this 32 by 32 to keep everything in tractable size. So this gives the size of our unknown. So what we just had, capital M would be 2 to the power of j in this case. Maybe we can actually use it here. We could say M equals 2 to the power j and n equals m times m. So that will be our size of the unknown, because in the matrix A, in the computational model, the matrix A, it contains both the size of the unknown and the size of the data, the k and n. They need to be specified by us. So now we have some angles for tomographic projections. So here we have a collection of those. Then we evaluate some then we build our matrix column by column. There's also taking a look case, but I think we will just comment that. And then we save it because this is something really time consuming to do this part. So let's compute these matrices for a collection of different sizes and then save them all with the file name containing the size information. So first of all, let's do this directory. If it's not there, let's make it, and then let's build a parameterized command for the save. So let's do it in this way. So we want to save to a file something like this, but now we want to keep the information of the size. So let's have here number to string j. So this will specify the size of our phantom, the power of 2 we are using. And I think, let's see, how do we choose the angles? Now we are doing just the number of angles in the rotation around the whole object. So the full 360 turn, and how many angles do we have in that range. So let's keep this and let's use this number of angles as our. Obviously, this does not now describe possible collections of angles like we just did with different densities of the angles and all that, or limited angle or stuff like that. Let's not care. For now, let's just use this number of angles. That's a uniform collection of angles over the full circle. So we have the size of the unknown recorded. Then let's put in this n_ung. That's the name of the file, and in the file, what do we want to put? At least the matrix A. And let's see. Let's put n_ung and angles. Let's put all of these j, m, n, just for easy further reference. So let's put here j, m, n, this one, and the angles. Oh. So now I have this huge save command thing, and then I evaluate it in MATLAB. So now let's just run this thing. Maybe let's run it with the smaller one so that we can, it doesn't take a long time. And let's here also, let's monitor how the run is going. So what is our I? Let's say Okay, let me run this. So now it already ran. Why? Okay, and the directory, I'll just put it away. Okay, so it's pretty fast to compute, and we now have in our data folder, we have our radon matrix with j equals 4 and number of angles equals 13. So later we can just load this one, and then that's our geometry, what we are using. So now if we want to do something else, for example, do the one we were thinking about, j equals 5 and this equals 33. Let's see how long this takes to run. There it was. Not too bad. And now we have here 32 by 32 unknown and 33 angles. So this way we can build up a collection of matrices like that, and then let's also compute the singular value composition. So actually let's still remove these two things we computed and compute the singular value composition as well. So we have this u d v equals svd of a, and let's put here also display computing svd, because that can take a long time. It's nice to know how long are we doing, so let's also clock it, tick, and then display spd svd computed in TOC seconds. So we can have an idea how long we have to wait for these things. And then let's also save there the SVD. So UDV. Okay, so let's, oh, SVDS. Well, actually let's do this for full matrix A. 0.6 seconds, not too bad. And let's plot let's just plot the diagonal of S, D. Or maybe we should use the semilog logarithmic scale. So it seems we are dealing with some kind of an ill-posed matrix. The singular values are smoothly going to 0 or becoming small, and also we can take a look at our matrix. So it looks very much like the thing we saw in the slides. Now we can zoom in a little bit to see that these are not really lines, these are points. If I zoom in, you see these are really non-zero elements in the matrix. Okay, and then I think we can do our first reconstruction still. So let's save this by the name let's say this one, and let's say this is first truncated SVD comp. I'm saying first because we are committing inverse crime here, so that's why first. We will do a better one later. But let's save that and start by sorry. Let's put here try truncated SVD for tomography. So then we choose again the size of the unknown with J. We choose the angle and then we actually just take in so now we load no, sorry. So now after this one we will have all of these. So now we can build our phantom. So here we have this tomodata test. So we can evaluate the phantom, create a sinogram. We can do it with two types of let's take everything here and go back to our SVD comp. So this would be recon 1. And I think we have the angles. It's called angles. Angles. Oh, but they are given, so we don't need that. We don't need that at all. M we have coming in from the loaded data, so we do the phantom. Then we do the sinogram using angles. And here, note, we are committing inverse crime. So we do the, oh sorry, let's do this now with our matrix A times this image dropped as a vector. So this should now be doing the same thing. Let's remove this one. Okay, so we have our M now done with the, let's call this F. This is F. So now we are doing inverse crime. We are simulating our measurement data using our computational model. And now we should use truncated singular value decomposition. And actually, let me steal our old code for that we did in deconvolution. Did we do it? I think we did. Did we? Yeah, here. Compute reconstruction. We don't have noisy data, we just have M. Let's see, we have this one.
You've got to paste the S-Vels thingy from the previous file.
Yes, let's take S-Vals is diag of D. And here we should have reshape F in the size mm, and here we should have reshape F0 to the size mm, I think. Let's see what happens. Okay, why? Let's see the sizes. Okay, that's fine. Seems okay. This seems to have a wrong size. Yes, because our matrix is no more, matrix A is not square in this case. So actually, we need here, we need to transpose this one. Otherwise, the sizes don't match. And here we have our truncated SVD reconstruction from 33 angles. And now, of course, we can use some more. Actually, let's take the, we have here the singular values. Let's take a look at the singular values. Okay, so let's put here F size. What was it? 32? Yeah. Sinogram. Oh, okay, yeah, so here should be, let's just not have that. Okay, so now you see we are using only very few of the first singular values. I think we can use some more. Maybe we could use you see, if you see here, I think we would maybe go up to this first tick mark here. What is it? 200. Let's see what happens with 200. So now we are using 200 of the first singular values, and we get a reconstruction like that. So now we have, for tomography, we have now built our model A times F, the matrix vector multiplication model. I hope not to have dropped you too badly out of this, because I know some of this just went on with coding, but anyway, you will have a great chance to get to know these matrices and objects yourself with the next exercises. Okay, I think that's pretty much it for today, so see you on Friday.